Hi everyone, this is Krishna Malgupati. Here I am handling power electronics circuit. This course is very useful to the electrical engineering people. And in this course, I am going to in today's class is introduction of power electronics, difference between analog electronics and power electronics, scope of power electronics, applications of power electronics, and finally different modulators, power modulators available in power electronics. We'll see these topics one by one. First of all, we'll see the introduction of power electronics. Basically, power electronics embraces the study of power engineering, electronic engineering, and control engineering. Means this power electronics is associated with three basic terms. Those are power, then electronics, and control. Means these power electronics are there for handling the major power, not the milliwatts of wattage of power. So we'll see them later. But basically, power. When we see the power having the four different types of terms that we can say: generation, transmission, distribution, finally utilization. Means what? The electrical power is going to be generated in the generating power plants, and it has to be transmitted to the load centers, because the load centers are available at the far away from the generating points. Thereby, this generated electrical power must be transmitted through transmission lines, and after that, it's going to be distributed, and finally, it has to be utilized at the load centers. Means what? This whatever the generally the generating voltage are in terms of 11 kV, 13 kV levels only. But what happened in case of transmission? We have to step up the that generated 11 kV and 13 kV up to 400 kV, so that it has to be transmitted with the less amount of losses, and after that at the distribution centers we are going to reducing the voltage levels from 400 kV to 11 kV, and after that this 11 kV is further stepped down to the uh, 440 volt if it is 3 phase, or 220 volt if it is single phase. Like that, we are going to step down the generated voltage for the utilization at the 11 kV or 440 volt for 3 phase, or 220 volt for single phase. And after that, we are going to use that voltage for the our commercial loads, this our domestic loads, and etc. And when we see the electronics, in this case, we are going to handle solid state devices, and some electronic circuits, which are going to be useful for the power process, electronic circuits, and some signal process. Signal process means it's not for the analog signal processing, it's for high power applications. We are going to use a signal process. And in this case, when we see the control, here also we are going to have dealing the steady state characteristics, and dynamic characteristics. Steady state characteristics and dynamic characteristics means what? So when you go for the controlling things, we are going to see the steady state characteristics of different types of solid state devices, how they are going to be behaved, and what is the nature of the switching devices, and what is their dynamic characteristics, so why they are going to be operated. And when we see the difference between the analog electronics and power electronics, so basic difference between the analog electronics and power electronics is basically electronic circuits are two types. Electronic circuits, two types. One is signal level electronic circuits, signal level. Second one is power level electronic circuits. Signal level electronic circuits and power level electronic circuits. Signal level electronic circuits are handling different voltage values, different current values, different power values. The range of the voltage values that the signal level electronic circuits are handling, few millivolt to some voltage values. Few millivolt to some voltage value. When we see the current values from few microampere to few milliampere, not even ampere also, means signal level electronic circuits are handling few microampere current to few milliampere of current only. When we see the power level, it is from few microwatt to few milliwattage. So, like this, the signal level electronic circuits handling only few millivolt to volt level voltage values, and few when we see the current values, few microamperes to the few milliampere current values. When you see the power, few microwattage to few milliwattage of power. When you see the power level electronic circuits, what we call the power electronic circuits, they are going to be handling the voltage values, several voltage value to thousands of voltage value, several voltage value to thousands of voltage values. When you see the current value, it is also from few amperes to kiloampere, few amperes to kiloampere. When we see the power from wattage value to from some watts to kilowatt or kilowatt or sometimes gigawatt. When we see the application of power electronics in case of HVDC system, those power electronic circuits are handling gigawattage of power that is going to be generating from the generating points. And let us see the scope of power electronics. These are the things which we have to remember forever, because many people can ask you the difference between the analog electronics and power electronics. At that time, we are able to answer for that question, because of this basically this is also an electronic circuit. But what happened here is the devices which we are using in case of signal level electronic circuits and power level electronic circuits are defined. Means the doping which we are going to use for the making of semiconductor devices is going to be giving us that for which we are going to use the semiconductor devices. Means suppose the doping levels are very low, we are going to use the that devices to the signal level applications. If the doping level is more and more, then we can use that switching devices for the power applications because they are going to handle the gigawattage of power, some kilo ampere of current values, some thousands of volt values. That's why this is very important to know the difference between the signal level electronics. See the scope of power electronics. Basically, power electronics plays vital role in electrical engineering, as I said earlier. And without power electronics, there is no electrical engineering nowadays. Why? Because when you see any application which is regarding to power, there must be power electronic circuits. Let us say simply, which we are saying in daily life, mobile charger. Mobile charger. Nowadays, without mobile, nobody is there. Everybody using mobile. Thereby, it has to be charged daily almost all. Means the battery which is there inside the mobile has to be charged, but the battery is need 5 volt of DC, 9 volt of DC like that. So to charge that battery, we need to use the power electronic circuit. Not only the mobile charger. Suppose we want to, in olden days, what happened in case of ceiling when we use, when we regulate the speed of the ceiling fan, we have a big box at the uh, switching board. But what happened nowadays, we are getting the power electronic controlling based circuits, which is like a small, when you see the ceiling fan control. Ceiling fan control, we are olden days. This much of box will be there for the what we call rotating the fan for the different speeds. But what happened nowadays? We are going to be replacing this type of system with a small power devices, which is going to be controlling the whole speed of the ceiling fan. Nowadays, not only those two, so without power electronics, there is no power applications existing in this society. When we see the applications, these two are one which are related to the our daily life. Not only this, when we see the technically for the electrical engineer, let us see one thing is here. Suppose we have different types of motors, AC motors, DC motors, and we are using these two different types of motors in industrial applications to drive the different types of mechanical loads. So suppose we want to control the different that motor. In the initial days, what we are going to use is we are going to use the um, ancient methods. Suppose you want to convert the AC power into DC power, AC power into DC power. In olden days, generally we are going to use the directly we are going to generating the DC power by using DC generator. DC generator. This DC generator application is there in generating stations because basically our AC generator which we are using in generating stations is synchronous generator. Synchronous generator. So basically this synchronous generator is a doubly fed generator. Doubly fed means it needs two inputs. One is a main input and the other one is auxiliary input. Here the synchronous generator main input is mechanical input. Mechanical input through turbine we are going to give mechanical input. Okay, other one is the second one is electrical input. Electrical input in the sense to excite the field winding of the armature circuit. We need to supply the DC power to the field winding of the generator. For that, we need to give the DC supply. So, how do we get the DC supply? It's very easy to convert the AC power to DC using only DC generator in old days. So, here we are using DC generator to feed the DC supply to the field winding of the synchronous generator, so that the operation goes very quietly and will get the electrical output from the synchronous generator. Electrical output. This is a DC supply through the DC generator. But what happened here is, when we see the DC generator, it's a rotating machine basically, and it is going to be occupy the huge amount of place, nearly like a big room. And the cost, when we see the cost of the DC generator, it is very high, high cost. And so the thing is that after developing the power electronics, we are going to convert the AC power to DC very easily without using any rotating machine like DC generator. That's why here we are going to replace this DC generator with rectifier circuit. Rectifier circuit. Rectifier circuit means we are going to replacing this old and traditional method that the DC power is feeding to the synchronous generator with the help of DC generator with the rectifier circuit. This rectifier circuit consisting of this power electronics configuration. One application is that. The other one is when we see the DC motor. Suppose in many industries, DC motor we are using for feeding the mechanical power to the mechanical output to the different loads, and one DC motor, you can say DC motor. From this we are getting output, and there we are connecting one load. Okay. Then let us take one DC shunt motor, right? And we are feeding to this one is terminal voltage, right? This is the armature current, and you can see this is the shunt field current, RSH. This is a 220 volt DC supply. Generally, the circuit is like this. Okay. So whenever the electrical power is given to the one DC motor, this DC motor will convert that electrical energy into mechanical energy, and it will drive the connected load like that. Suppose when we see the speed of the motor, let us see. As we know some equations of the DC motor, those are EB equal to ET minus IR. When we avoid the brush stroke, we are getting the equation like this: EB equal to VT minus IR. As we know, EB in terms of operational values, EB is equal to K phi omega. We know that this phi is a flux and this omega is angular speed. Angular speed in radians per second. So when we replace this EB in this equation with the help of this K phi omega, we will get K phi omega equal to Vt minus IRG. From this, what we have to observe here? Omega. This omega is what? Angular speed of the motor. So we have to get the relation for omega. Omega equal to Vt minus IARA upon K phi. So this is the basic equation where the speed of the DC motor concerned. It is few terms that we have to remember. One is terminal voltage, other one is armature current, armature resistance, and this is a constant factor. This is a flux of the motor. Let us consider one factor in this case, the relation between the omega and phi. Here is omega is inversely proportional to the flux produced. Okay, and there is one more relation between the flux and current flowing through the shunt field winding. Means what? If you vary the current flowing through the shunt field winding, automatically the flux produced in the motor is going to be varied. That in turn changes the speed of the motor. This is the one concept that what generally we are using in DC motor. Suppose you want to change the current flowing through the winding, means this current has to be reduced or increased. Then what generally we have to do? Only option is based on the Ohm's law. What is that? ISH equal to Vt upon RSH. Suppose we want to change the current flowing through this winding, means reduce it. If you want to reduce the current flowing through field winding, we have to increase the shunt resistance. Means what? We have to add the additional resistance in series with this shunt resistance. Due to that, what is the disadvantage? If we add the external resistance to the existing resistance, the losses, ohmic losses are going to be increasing. The first point is that. The first disadvantage. If we increase the ohmic, if the value ohmic loss value increases, that will going to be reduce the efficiency of the system. As we know, efficiency equation, output power by output power upon input power. So when we write the input power in terms of output power plus losses, let us say output power plus losses. Very simple. Means what? What is the relation between efficiency and losses here? Very simple. Efficiency is inversely proportional to losses. Indirectly saying that the input power is caused to produce both output power and losses. If the losses in the motor increases, means output that we are grasping is going to be reducing, where the output power is directly proportional to the efficiency. Efficiency is also going to be reduced. This is the main disadvantage in the system. Thereby, we couldn't do that. The additional resistance we couldn't add to the existing resistance RSH. What we have to do for the varying the shunt current? Very simple. Here we are going to use one power electronic converter. When you use power electronic converter, what will happen? Let us see here. Instead of providing the constant DC supply, instead of providing the constant DC supply, what I am going to use is I am going to use one power modulator here. Let us take one power modulator here. I am roughing this. Instead of varying the shunt resistance by adding external resistance to this RSH, I don't touch this RSH. I want to change the current flowing through shunt branch. Only option is by varying the terminal voltage. Now what I am doing is, suppose I want to reduce the current flowing through the shunt branch, I just vary the terminal voltage by reducing it, because shunt current which is flowing through shunt branch is directly proportional to the terminal voltage. That's why I'm going to reducing the terminal voltage. Means what? Instead of providing the fixed DC supply to the motor, DC motor, what I'm doing is I'm going to supply the variable DC supply to the motor by keeping one PPU, power processing unit, in between the fixed values and variable values. What we call this power processing unit. This power processing unit consisting of power electronic configuration. Means some power solid state devices are connected in different manner, different configurations to get this power processing unit for the optimized values of the what the motor required. Let us see. So here at the input to the power processor unit is fixed DC supply. From this fixed DC supply, this power processing unit is going to be giving us a variable DC output. Variable DC output. Suppose my DC supply value is 220 volt, but here when you use the power processing unit, we are getting 200 volt DC supply. Thereby what happened? We are going to reducing the terminal voltage from 220 volt to 200 volt. Thereby current flowing through the shunt branch is going to be reduced. So that what happened? The flux produced in the motor is also going to be reduced. Let's see this. When we reduce the current flowing through the shunt branch, we reduce the flux produced in the motor. If it is reduced, then what happened? The speed of the motor is going to be increased. Suppose initially our motor is running at 1200 rpm. After doing this process, our motor will reach its rating value 1500 rpm like that. Means what we are calling here is this is one of the power modulator. This is what we call the other name for power processing unit is power modulator. Modulating the power. Power electronic circuit which is used for modulating the power is nothing but the power modulator. So other name for this power modulator is power processing unit. See, very simple. When we consider this different power modulators means it is one of the power modulator where the fixed DC supply is going to be variable DC supply using one power processing unit. This is what we call generally DC to DC converter. DC to DC converter. The other name for DC to DC converter means chopper. Chopper. Exactly saying it is DC chopper. And means what? Fixed DC is going to be converted into variable DC. Suppose DC supply is not available. Suppose DC supply is not available. In the nature, AC supply is available because the electrical power which is going to be generating is in AC nature. So it is available in two forms. One is in three-phase form, other one is in single-phase form. Okay, and when we see the three-phase form, let us see this AC power supply which is available. So when we have not having any DC supply source is not available, then we have one more option is that AC supply is available. AC supply, I am using here single phase 220 volt 58 AC supply, but our motor required DC supply here. Okay, let us take variable DC supply that the motor is required. Then I am going to use one power processing unit to convert this AC power supply into variable DC power supply for the DC motor. So then what we call this PPU, power processing unit here? Very simple. Fixed AC is going to be converting into variable DC. Means what? AC supply, AC electrical power is going to be converted into DC power. Here we are using PPU called it is AC to DC converter. AC to DC converter. Okay. The other name for this one is AC to DC converter. Other name for this one is rectifier. Rectifier. What does it mean? Rectifier means rectifier is a power converter which converts AC power supply into DC power supply. And here in this application, that DC power supply is going to be utilized by the DC motor. Means what? Two converters, two modulators we discussed. One is a DC chopper, other one is rectifier. Okay, with these applications, we can say these two are very useful. For example, when we take the other type of motor, which is very useful in industrial applications, is called induction motor. Induction motor is a AC motor, and induction motor almost 90% of industrial loads are runs based on the induction motor. So let us take one induction motor here. One induction motor. I am taking one induction motor. This is my induction motor. And it is connected to some external load, mechanical load, and it is having some speed, and it is supplied with some AC power supply. It is AC power supply. Basically, three-phase induction motors are using very much, and three-phase 440 volt 50 Hz AC supply is applying to the three-phase induction motor. As we know, three induction motors are different types, so not require that. So induction motor is supplied is going to be converting the AC electrical energy into mechanical energy, whereas DC motor converting DC electrical power into mechanical energy. Whatever may be the nature of the electrical power, but output is mechanical power based on the different type of motor. Here in this case, it is AC motor. AC motor means which is runs based on the AC power supply. Okay, but suppose you want to change the speed of the induction motor. Let us take one more example here. Suppose I am connecting one here and controller. This is what we call controller. Speed controller. Let us take. There exist generally two types of controllers at the output side between the induction motor and the load. One is speed controller, other one is current controller. Current controller means one is mechanical parameter controller, other one is electrical parameter controller. So what we call this is going to be compared with some reference value. This we are going to controlling control circuit. We are placing this control circuit output is given to some PP. Let us take this. In between the source and in between the source and motor, we are using one PP. This is my PP. Okay, look at this. This is my PPU in between the fixed source and motor. And I am going to use one controller. We are taking some reference from the output. Okay, this is given to PPU side. Suppose our motor is running at 200 RPM, but it is reference is 1500 RPM. Means the load requirement is 1500 RPM. Very simple. The load requires 1500 RPM, but our motor, induction motor, providing to the load, the speed is 1200 rpm. Means what? If our motor rotates with the 1200 rpm, the load is also getting the 1200 rpm. But the load requires 1500 rpm. Means what? We have to change the speed of the induction motor from 1200 rpm to the 1500 rpm. So therefore what happened? We are getting one controller here. So we are going to compare with the 1200 rpm with the fixed value 1500 rpm. It means there exists some mismatch values. This control circuit will sense the PPU circuit. Means it is not up to the mark that the induction motor is providing the speed to the load. That's why I have to change the speed of the induction motor to reach the 1500 rpm like that. Whenever this induction motor output is 1500 rpm, it increases to 1500 rpm. So it matching to the 1500 rpm of the load and it is matching to the 1500 rpm of the reference value. This control circuit won't send any signal to the PPU circuit that this PPU circuit will think that if the signal is not getting from the circuit, control circuit, exactly values are going to be induction motor is going to be given to the load. Like that, this initially what happened, why I am trying to tell all these things means, when you give these fixed values to the induction motor, the induction motor couldn't able to provide the or produce the exact values required by the load. At that time, we are going to change the values of the output from the induction motor by using one PPU in between the source and induction motor and taking some reference from the output side and going to be analyzed here. Then the PPU will send the signal, will provide the input to the induction motor to produce the values required to that particular load. And let us say this. When we see the power modular type, the type of the power modular in this case, in this application, the induction motor requires, let us say AC. We can say particularly variable AC. Variable AC means what? The PPU, what we place in between the induction motor and source, is going to be converting that fixed AC values into variable AC values. Then we can say here one power modulator called AC, fixed AC into variable AC, fixed AC into variable AC. This is one type of a power modulator, and we can say this one is AC voltage controller. AC voltage controller. Other name for fixed AC converter, fixed AC to variable AC converter is called AC voltage controller and cycloconverter. Cycloconverter. Why? Because we are going to handle the two different types of converters for the converting fixed AC into variable AC means. Here in this case, AC is a vector quantity as we know, and it having the magnitude and frequency. Magnitude and frequency. Okay. Suppose you want to change the magnitude values at the output side, the PP using for that one is AC voltage controller. The other name for AC voltage controller is AC choker. Other name for AC voltage controller is AC choker. Means fixed AC value in magnitude is going to be converting into variable values, variable AC value in magnitude only without change in frequency value. Means it's going to be changing the y-axis values, not the x-axis values. So other type means we are keeping the y-axis values constant, means magnitude is going to be constant, but the frequency of the signal, frequency of the AC supply is going to be variable. For that time, we are going to use the cycloconverter. Cycloconverter. The name itself suggesting something. Look at this. Cycles. What do you mean by frequency? Frequency defined as number of cycles per time. Means what? Cycles are going to be changing. Increasing the number of cycles, reducing the number of cycles. Means x-axis is going to be changing. That means frequency is going to be changing. Suppose one application requires constant magnitude values, but the change in frequency. At that time, going to use cycloconverter. Suppose some other application requires change in magnitude values, but not change in frequency. At that time, we need to go for AC voltage controller. So, best example for this AC voltage controller is fan regulator. Nowadays, we are using very much. So, this is the third type of power modulator in case of different modulators. The other one is, which we can say, fourth modulator is, for suppose AC supply is not available. AC supply is not available, but our induction motor requires AC supply. Then look at this. I have DC supply. 220 volt DC supply. Right? So this DC supply must be converted into variable AC. Okay? And look at this. We are placing one PPU, power processing unit, to convert this fixed DC values into variable AC values, because the induction motor requires AC supply, a variable AC supply. At the time, the PPU is called, it is going to be used what? Fixed DC converting into variable AC. Variable AC. In this case, the converter is called inverter. Inverter means inverting operation takes place as compared to rectifier. In case of rectifier, what happened? Fixed AC is going to be converted into variable AC. The same thing what happened here? Inversion operation takes place. Fixed DC is going to be converted into variable AC. If you have DC supply is going to be converted into variable AC and giving to the induction motor. Thereby, induction motor will generate the mechanical energy and it is given to the load. Like that, we are going to use one PPU in between the source and motor. And this is the fourth type, inverter circuit. These are the different types of power modulators. So far we discussed. We'll see finally altogether what are the different types of power modulators. So the entire power electronics syllabus we are going to discuss in the different types of power modulators. Only first unit will give us solid state devices discussion. After that, all 4 units we are going to discuss the different types of power modulators. So finally, I am concluding here. Different types of power modulators. First one is AC to DC converter. AC to DC converter. We are calling this one is rectifier. Then DC to DC converter. DC to DC converter. The other name for DC to DC converter is DC chopper. DC chopper. The third one is DC to AC converter. This is called inverter circuit. Inverter. So finally, AC to AC converter. AC to AC converter. There exist two types. As I said, AC voltage controllers and cycloconverters. So these are the four different types of power modulators available in the power alternators, and